mini lesson can be recorded for posterity. So I'm going to stop sharing my screen and let's go back. Oh dear, stop that. Okay, so here is a cool little random toy. And what I'm going to do is these three balls are kind of fixed. You can see perhaps that there's a little bit of a nub right here so that these balls can't actually come off. These guys, on the other hand, can, all right? And so what I'm gonna do is ask you to make a little prediction. I'm gonna sort of zip the camera away just a little bit. I'm gonna drop this guy from a little bit of a height up here. And I want you guys to think about what's gonna happen when this guy hits the tabletop, remembering that these two guys come on and off pretty loosely, right? The other three do not. And if I can get myself out of the way so you can see it pretty clearly, all right? And if I've done all this right, please, 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 let's see, it goes really quickly, so we'll count it down here. Plus the SpaceX rocket goes this week on Thursday for those of you that are completely physics geeks. I'll remind everyone about that. Thursday, we got the countdown for SpaceX. So we'll go 3, 2, 1. Holy moly. I do not know if you could even capture that. Did you see what happened, Addie?
Did the little red ones fall off?
One little red one shot off at great speed, okay? Because literally it's now rolling around the floor, all right? So the point of this is just, if we were all together in class, it's pretty cool. It's a little hard to do this in my tiny little space with my camera. But what it does is it illustrates an important point about what we're going to be talking about here. So at this point, it would be helpful for you guys to jump over and maybe jot down a couple of things here that I'm getting ready to write down. And the point of this sort of next, and this is our final unit for physics here, is this unit's all about momentum, all right? And so first off, we want to get sort of an idea of what momentum is. And we already have a feel for this, I think, in terms of, you know, sportscasters will say that a certain team has the momentum going into the half. So I'm gonna put it on you guys here. Let me go over to Annie. Annie, I'm gonna ask you, when you think of the word momentum, just give me your sort of off the cuff definition. What does it mean?
I don't know, kind of like speed almost, but
Okay.
like a continuation, like that builds up, like a built up speed, I guess.
Okay. It's definitely related to speed, and we're going to go ahead and use the fancier physics word velocity. All right. And so if something is moving fast, it's probably got a lot of momentum. If something's moving slowly, it probably doesn't have much momentum. So velocity definitely plays a role. Annie, I'm going to come back to you here. Do you think that there might be anything else that is related to if something has a lot of momentum? There may be something else there. I want to see if you can come up with it. It's okay if you can't, but I want you to at least try.
Maybe a lot of force, but like force upon impact, maybe
Okay.
something like that.
You're getting warm. Let me give you an example here, and I think you're going to get it. If I were to compare myself, I weigh about 200 pounds, Annie, versus let's say a NFL linebacker who weighs about 330 pounds. And both of us are coming at you, and we're getting ready to tackle you. Who is going to have a little bit more of an impact on you?
Probably the linebacker.
Yep, yep. So what I'm getting at here is not only is the velocity important, but it's also the mass of the object, okay? And so when we're talking in physics, all right, momentum is going to be equal to the mass of the object times the velocity of the object, all right? And Annie, thank you for doing that. Now I'm going to go over there to Emily. Emily, we did some stuff with mass and velocity a while back. Can you think of any topics where we said, hey, you know what, if I know the mass and the velocity, I can figure out the blah, blah, blah? Putting you on the spot here.
I don't, I want to say like inertia.
Okay, inertia definitely related to mass.
Is it the force? No.
It starts with an E.
And no.
Say it.
Energy?
Yes.
Okay.
Yeah, no. It's like we're coming off Memorial Day weekend. This is why am I even asking questions? It's ridiculous. I'm sorry, Emily. So
We're
no,
all
in all,
done with school by this point.
what's that, Anna?
We're all just done with school by this point.
Yes, we are, but you guys are still here and you are my superheroes. So look, if you recall, or maybe you don't recall, all right, this is just a little aside. Kinetic energy was another thing that related to mass and velocity, but that was a formula of 1/2 mv squared. So I mention this simply because we'll be revisiting it during this unit, but not so much today, okay? So first off is to understand that momentum is a pretty simple quantity. If you know the mass of the object and you know the velocity of the object, you know the momentum of the object, all right? So I've got Anna on my little screen here in the camera. So Anna, what do we measure mass in? Let's talk about the units for momentum.
Kilograms?
Yeah, mass is typically in kilograms when we do our old metric system. And what is velocity? What are the units for velocity, Anna?
It's meters per second.
Yep. So when I multiply those things together, nothing really cancels out. So I end up with this weird looking like kilogram meter per second. And that would be the unit for momentum, kilogram meters per second. All right, so momentum, pretty straightforward idea. If I have a big old Mack truck driving down the road and I say that the Mack truck is 1,000 kilograms and the velocity is 1 meter per second, if I wanted to know the momentum, it is this easy. The momentum would simply be the 1,000 kilograms times the 1 meter per second, picking easy numbers so that we can kind of ease into this stuff. 1,000 kilogram meter per second, all right? Now, the bigger part of what I want to get at today, and it'll only take a couple more minutes here, guys, so I appreciate you guys sticking with me here. We're going to take a little journey, and that journey involves going back to F equals ma. All right, now let's see here. Who have I not put on the spot yet? Addie, I'm going to come over to you. Addie, I need some help here. There was acceleration means something. Can you tell us what acceleration really is? What the definition is or what the formula might be for it?
Wasn't it like velocity per second or like something?
Very, very warm, all right? Acceleration is, if you're accelerating, Addie, what must be changing?
The velocity.
The velocity. So acceleration by definition was your change in velocity over time. So you were really close there. It was velocity over seconds, yes, but it's the change in velocity. So what I'm going to do here, and this is just going to introduce the next little thing that we do, because momentum is, it's just an idea. An object can have a lot of momentum if it has a lot of mass and a lot of velocity. But more interestingly enough, we want to attach it to something else here. So watch what I'm going to do. Since we know F equals ma, and we know that A is equal to delta V over T, all I'm going to do is take this and do a tiny bit of algebra, and I'm going to multiply the T over, and I'm going to end up with this expression right here. And this is a biggie, and we're going to explore this in this last little unit here. So let's go back and reflect on this. Addie, I'm not letting you off the hook yet. What does F stand for?
Force.
Yeah, and what do we measure force in? Oh,
Can't remember.
starts with an N. Sir Isaac
Newtons.
Newtons. Okay, so we've got newtons here. What does T stand for?
Time.
Time. And what units are time usually measured in for us?
Seconds.
So I've got newtons times seconds, right? And then we've got mass times, now this is looking a lot like, and sorry, I'm a little bit off my page there. So M stands for mass, Addie, and then finish it up here. What does delta V stand for? The delta means?
Change in velocity.
Yeah, so this is change in velocity. All right, So let's put some names on this, and then we're going to pretty much call it a day here, because I think one of the things that I'm learning about this is your attention span is really short when you're doing video stuff. And so we've got to keep this thing moving along. Addie, thank you very much for that. If I go over to Jennifer Overdahl, Jennifer, can you tell me what the unit is for mass that we typically use?
I'm sorry, what was that? I didn't hear what you said.
That's okay. What is the unit we usually use for mass?
Grams?
We
No.
can, but a little bit bigger.
Kilograms?
Yeah.
A
So we want to stay in kilograms. And then what is the unit there, Jennifer, that we usually have for velocity?
meters over second?
Yeah. Okay. All right. So Jennifer, thank you. So what we've got here is this new formula. All right. And we just said that mass times velocity was momentum. So if I talk about mass times change in velocity, this side of the equation ends up being not momentum, but the change in momentum, right? And so when an object undergoes a change in velocity, it's undergoing a change in momentum. Now, what causes an object to change momentum? Well, you exert a force on that object for a certain amount of time. This side of the equation also has a name. Force times time is called impulse, all right? And so these are big ideas, and they're so big that I'm going to give them their own page here in just a second. So if everybody is okay, speak now, forever hold your peace, because I'm going to move the page here.
I have something.
Yeah,
Just
okay,
to clarify,
Mhm.
we went from mass times acceleration to mass times, so for change in velocity, is
Mhm.
that, are we saying that that's just velocity within?
So we're going to do a little bit more with that in a second, Kate, but in essence, are you okay saying acceleration is this? It's the change in velocity over time?
Yeah, I just like,
Okay.
if we started with mass times acceleration, I'm confused how we ended with mass times velocity based on the units.
Because, let's see here. Okay, so if I look at so are you looking down here and you're like,
Yeah.
there's no way those make sense?
Yeah,
Okay, here's why, and this is a great question. Newtons, remember, comes from mass times acceleration, MA. And so that means that a Newton is a kilogram meter per second squared. Scoot that up. So if I take this and I multiply it by seconds, the seconds goes away, and now look at what I'm left with. Kilogram meters per second, kilogram meters per second. So they actually are the same thing, Kate. They just look very different, don't they?
Thank you.
Does that help?
Yeah.
All right, great question. All right, and so now let's get this all wrapped up in a nice, neat little package for next time. So Ft equals m delta v. So this is often referred to as the impulse momentum formula. And what it is really telling us is that if I want to change the momentum of an object, right? So since this side, so to change the momentum of an object, which in essence means speed it up or slow it down, change its velocity, to change the momentum of an object, exert an impulse. All right? And remember, impulse is this force times time. Now, when I dropped, just to kind of bring this all back full circle here, when I dropped my little toy, all right, I'm trying to see who I've not picked on yet. I think I've gotten everybody here. Oh, no, I could pick on Kate just a little bit. All right, Kate. So look, when I drop this thing, all right, it's speeding up, speeding up, speeding up, speeding up. It hits the table, okay? When it hits the table, does this experience a force?
Yes.
Absolutely. And does that force occur over a long time or a short time?
Short term.
Yeah, it's a very short amount of time, okay? And so this thing experiences an impulse. Now, would you say that the velocity of these objects changed pretty dramatically? This guy fell at some speed, and remember what the little red ball did, right? This guy came shooting off. So did this guy experience a change in momentum?
Yes.
Yeah, right. So what we're going to be doing in this unit is learning how this formula actually explains all kinds of things, okay? And so what we'll do is we'll leave it with this. The thought that I want you guys to consider is if I drop an egg onto concrete, we all know what's going to happen. So here's my egg. But if I take that very same egg from this very same height and I drop it onto a big, fluffy foam pillow, is there a different outcome? Well, the answer is yes, obviously, right? And the reason for that isn't so much that the concrete is hard and the foam pillow is soft, but it has to do with this formula. And so that's where we'll kind of pick things up with next time. So I'm going to go ahead and stop the recording.